So welcome to the new lecture of digital control system. In this lecture, we will discuss about some basic discrete time signals which are used in digital control. So to start with, uh, there are certain test signals which are used in digital control system. Instead of using the word signal, we generally use the word sequence basically. So some discrete sequences are used. Like in continuous time system, we have certain sequences. For example, we have unit impulse, we have unit step, we have ramp, we have exponential, we have sinusoidal. So there are certain signals, test signals, which are available in the continuous time system or continuous form. That discrete representation of these continuous time signals, impulse, step, ramp, exponential, and sinusoidal, are available in digital control system for the implementation for the testing purpose basically. So the purpose of today's lecture is to understand such few discrete time signals which are used. So there are various basic discrete time signals which have a significant uh, or which are very important uh, part to play as far as the analysis of the signals and systems is concerned, because we are making use in digital control, we make use of the computer or a digital device. So it becomes important to understand such basic discrete time signals uh, as far as the digital control is concerned. Now, these signals are nothing but they are the discrete representation of their equivalent basic continuous time signals. And these signals are, we have unit sample sequence, we have unit step sequence, and then we have a sinusoidal sequence. So the first is unit sample sequence. Unit sample sequence is also uh, known as unit impulse, right? So the unit impulse sequence basically is a sequence which exists only at the zeroth sample. So it is generally represented by the equation delta k, as you can see here, which is equal to 1 for k is equal to 0. So that means it only exists at zeroth sample, otherwise it is 0. Means its value is 0 for all other samples except 0, right? So you can see here in this pictorial representation, the value of delta k is 1 at zeroth sample. Otherwise, at first sample, second sample, third sample, and so on, the value of delta k is 0. So all the values will remain 0. So this is what unit sample sequence is, and it is also known as I mentioned earlier, unit impulse sequence. So why are we calling it as unit? Because its magnitude is 1 for some sample k is equal to 0. Otherwise, we can also see it as a sample sequence or impulse sequence or impulse function also. So in that case, your delta k will be some value, let us say uh, A, for example, at 0 and 0 at all other sequences, right? In this way. So it can be represented as delta k is equal to A for k is equal to 0 and 0 elsewhere. So this means that we are calling it as unit because its magnitude is 1. Otherwise, for any arbitrary magnitude A, the impulse sequence or sample sequence can be represented by this particular formula. Then the delayed sequence, the delayed sample sequence. So if you delay the given sample sequence or impulse sequence by n samples, so in that case, your delayed sample sequence will be 1 for k is equal to n. Otherwise, it will be 0. So what you have done, you have delayed it. So now the magnitude 1 of the sample sequence will be available at k is equal to n only, otherwise it is 0. So it is shown here in the pictorial representation. Now if you see closely this one, so a sample sequence can be represented by this particular equation. So any arbitrary sample sequence, irrespective of its magnitude, so it is basically the sum of various uh, sample sequences and delayed sample sequences. So basically its common formula is this one, where Rn would be the uh, magnitude of the samples basically. So here this is, let us, this is R1 and this is R2 and this is R3 and this is R4 and so on, right? Now if you see R1, so this R1 is R1 delta k, right? So this is how you can write it, because delta k is available at zeroth sample, it is not delayed sample. Similarly, what is R2? So R2 is delta k minus 1. So when you have delayed the sample sequence by 1, so you have the sample whose magnitude is or whose amplitude is R2, and similarly R3 and R4 and so on. So that means this representation is basically, you can see the scaled sample sequence. These are scaled sample sequence. Okay, so in totality you have this one. So this you can say sum of scaled, delayed, right, sample sequence, right? So in this way, you can represent any arbitrary sample. For example, if you have a sample like this is some xk, for example, and there are some samples. So you have samples like this. This is one, and this is, let us say, two, like its magnitude is 2, then 0, then 3, like this. Okay, so this is 0, this is 1, this is 2, this is third sample, right? Now you can represent this whole representation as 1, like, and this would be xk is equal to x0. So this is zeroth value into delta k minus 0, plus then this is x1 into delta k minus 1 plus into x2 delta k minus 2 plus x3 delta k minus 3 and so on, right? So this is how you can represent. So what you are doing actually is you are scaling the sample sequence, and scaling means you are multiplying it with some arbitrary amplitude value, right? So this is what you are doing basically in this particular thing. So there are three concepts. One is sample sequence, which is here this one, and then delayed sample sequence, and then you have scaled delayed sample sequences, right? Now, the second is unit step sequence. So, what is a signal basically? So, if we have a step signal, so step signal is given by some, let us say ut, which is equal to some value a for time greater than equal to 0 and 0 for t less than 0, right? So this is for continuous time, right? This is for continuous time. In discrete case, or for discrete signal, we have step sequence. So step sequence is given by mu k, which is equal to some, let us say a for k greater than equal to 0 and 0 for k less than 0, right? Now if the amplitude a, so this a is nothing but the amplitude of the given step sequence, right, is 1, that is unity, then we call such step sequence as unit step sequence, right? So let us see how does it look like and how do we express this type of sequence. So a unit step sequence is represented by mu k is equal to 1 for k greater than equal to 0, that for all samples which are greater than and equal to 0, otherwise that is k less than 0, it is 0. The amplitude of this signal is 0. Otherwise it is 1. So because the amplitude is 1, so we are calling it as unit step sequence, right? So this is represented here. So a unit step sequence is 1 unity for all the values of k, right? Then we have delayed step sequence also. So a delayed step sequence is the one in which you have delayed the value or um, uh, or, or the step sequence by n samples basically. Okay, so this would be given by mathematically by this equation here. So k minus n. So minus n is that we have delayed by n samples, right? So it would be 1 because it is a unit step sequence or delayed unit step sequence. So its amplitude will be 1 for k greater than equal to n, otherwise it will be 0. So it is represented by this diagram here. You can see for all the value of k less than n, the magnitude or amplitude of the given signal is 0. Otherwise, it is 1. So this is a step. So you can see a step is being formed here. Okay. So this is a step. A step is being formed here, right? Okay. So that is why we call it as a step sequence. Sudden change, basically, right? Then we have the sinusoidal sequence. So a sinusoidal sequence is always given by some value xn, which is nothing but the sampled form of the xt, right? So the in continuous form or continuous representation, a sinusoid signal is given by a cosine omega naught t plus phi, right? But when it is sampled and converted into a discrete formation, so it is given by xn a cos any uh, omega naught. This is also omega basically. So omega naught n plus phi, where n is the number of samples, right? So uh, now, how did we get this representation here? When we have sampled the continuous time signal at some sampling frequency, which is fs, So the sampling rate of this signal will be Ts is equal to 1 by Fs, right? This is the sampling rate or sampling period basically. Now what is sampling period? It is the time step between the successive sample. So the difference between two successive samples is the Ts, right? Now this omega naught basically it is nothing but the angle increment of the given sinusoidal signal between the samples. So to what value the magnitude of the given sinusoid is changing, right? Okay, so its value is radians per sample and not radians per second. So radian per second is for omega naught, right? For this omega naught, it is always radians per sample, right? So this is we have in the lecture basically. So instead of these signals, we also have some more signals like we have the um, ramp signal, we have ramp sequence basically, we have exponential sequence. So in this way we have some more sequences also, right? So but these are the three basic sequences which we generally use in digital control for the testing purpose. So this was all about today's class. Thank you so much.